So first and foremost, I want to make sure that everyone has the materials that we require for this really, really long exercise. You should have a worksheet and you should have a zip file that you should not be able to unzip. You shouldn't be able to unzip it yet. No, what? What do you mean example 1? Day 2 materials, shark loader. Where did we list that? Did we put that anywhere? Oh, I mean it is but like I was gonna make a because forensics is part of incident response and analysis. I hope that was elucidated in the slides from last week, assuming you watched the video. Anyways, you should have a zip file. I mean, if you know the password to it already, then good for you. But like, I want to talk about it a bit first. Then you should have a PDF, which is a worksheet, right? So, just for a bit of storyline, right? And this is a realistic IR scenario. Your friend is trying to pirate a video game, then they kena infect, right? By the shark loader rat, the remote access Trojan, right? Made by Evil Gang. So we have a copy of the sample. We're gonna have network logs, and we're going to try and see what was done to their computer based off the network logs and based off how the malware operates. Okay, so first things first, I want to do a very short diversion and talk a little bit about how malware is distributed and analyzed, right? So, in the industry, right, how we collect and analyze malware at scale is using these things called aggregators and scrapers. So essentially, we will host servers where we intentionally download malware, right? We intentionally want people to hack our servers so that they put malware onto it, then we collect those samples, right? These are called honeypots. So the thing is, there are a lot of open source ways that malware are being collected and aggregated. For example, there is a website literally called Virus Share. What do they do on this website? They share viruses, right? So for example here, this is a virus that someone has uploaded to the database, and if you have access to the site, like you have like an account, a proper account on this website, you can download it and analyze it yourself. So for example, where I'm working at, right, sometimes we identify a certain class or family of malware, and then we want to find more samples of it to analyze, right? We're not going to aggregate all of those samples ourselves. It is often easier to go to one of these websites that already has a lot of them to look at it. Another thing to note is convention. So I'm going to go to another virus website called Malware Bazaar, right? So Malware Bazaar, this is another database, right? And something that's very interesting about this database, okay, I will emphasize this point again, the disclaimer that I did earlier today. If you download malware from here, you run it on your school Wi-Fi, then someone kena, right, because of it. That is a criminal offense, okay? You cannot anyhow download malware and run it. More for your own self-preservation also, if you want to analyze malware for fun, or you want to basically learn more about this at your own time, you can download samples from here to analyze. But if you run it on your own computer, and then your computer kena, no one can save you. I mean, you can save yourself, but like this is on you. Okay, the onus is on you. So for example here, we can see a lot of the things that we've been talking about actually. ELF files, right? So these are all Linux-based malware. We can see a lot of rats, right? DC rat, Remcos rat, ClickFix. If you remember from last week, ClickFix, the fake captcha, right? Which that tricks people, right? SH, WannaCry. We still got WannaCry samples in the big 2026, right? That's crazy, right? So what I'm going to do, which you guys should not do, this is the only part of the workshop where I don't want you to follow what I'm doing right now, right? I'm going to take a random malware sample and download it. See, I can do this because I'm a professional and I know what I'm doing, right? So something that I want you to notice is that the identifier for a piece of malware is a SHA-256 value. Does anyone know what SHA-256 is? It's a hash. What is a hashing algorithm? Okay, file integrity is one thing. So a hash for a file is a unique identifier for a file, right? If I give you two files that are both named the same thing and have the same file size, right? How do you tell that those files are equivalent? Yeah, they share the same hash. You see, traditionally, what you would have to do is you have to go byte by byte. You have to open both files, then go byte by byte, check. Yeah, correct. That would take really long. Like, that's ridiculous, right? So instead, what you do is you hash the file, which means you just take the file, you put it into this algorithm, and it produces a unique value. Then if two files have the same unique value, that means they are the same file. Does this make sense to everyone? Okay, it's like I was gonna say DNA sequence, but that doesn't really, not really. Fingerprint, I guess. Yeah. So that is what we're also seeing with what I've distributed to you guys. So the file name of this zip file is the MD5 hash of the malware sample that's inside, or well, the malware sample, fake malware that we're going to be analyzing, right? So this is to keep up with convention. I'm going to download a malware sample right now. So you see caution, blah, 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 right? This is to tell you that you will be liable for downloading malware. And I am, so I'm going to download it. Or like it doesn't run, right? Duh. So something I want you guys to notice is if I try to extract it, right? If I try to extract the malware, it is password protected. And you can see on the screen it says the zip password is infected. This is convention. This is conventional, and usually when people distribute malware to share with other teams or to share with other analysts, we will package them in zip files and we will always set the password to infected, right? This is standard procedure. So that is exactly what you guys are going to do as well with the malware that we have received, Shark Loader. I want you guys to extract this zip file, and the password is infected. Inside the folder, you should see 3 files. You should see this really long hash, right, which is our malware sample. You should see a pcat file, which is traffic captured from an infected computer, and you should see a Python script. Okay, does everyone see these 3 files? Okay. All right, let's go back to the slides. So the first thing that I want you guys to do is a bit of triage. So triage means initial pass of analysis and trying to understand some of the information that we have on hand, right? So what methods did we have to extract metadata, identify file types, and so on and so forth? What tools have we discovered over this workshop? Strings, some other tools that we've used. Okay, strings. Hex dump, one more very nice one for metadata signatures. Okay, Gedra is for decompilation, we'll use it later, but detected easy, right? That's another simple one that we've used. So this is before we were covering decompilation. So these are good initial passes to let us identify some important metadata and information about the file without even decompiling it or running it, right? So I want you guys to look at the worksheet, and I want you to try and answer the first question: what program does this Trojan attempt to masquerade as? So remember the context of this story. It is supposed to be a video game. So it's supposed to pretend to be a video game. Try and look through the strings, try and look through the metadata, try and look through some of the information of the file, and give me a video game name that is trying to pretend to be. I will give you 2 minutes. Has anyone figured out what video game it's masquerading as? Peggle. Peggle? Full legal name. Peggle Deluxe. Peggle Deluxe. Yes, correct. Okay, I'm going to do something reckless. I'm going to run the sample. So like just to simulate what the person that got infected would see, right? When you run it, you can see this is a fake crash dump, but the fake crash dump actually says what video game it is, Peggle Deluxe. You don't have to run it to see this. You can use our good old friend strings. And if you look through the strings, you should be able to see PopCap games, right? Futon, and then somewhere we should see Peggle Deluxe, somewhere. Do I see Peggle Deluxe here? I'm just gonna grab. Yeah, Peggle.exe, Peggle Deluxe, right? This is an awesome video game, Peggle Deluxe, right? So the initial recon that we can do, right? As we've mentioned and emphasized a few times, so I'm gonna emphasize it one more time, defined strings inside a binary are crucial in analysis because what we saw last week was that known strings can help us with library or program identification, right? String cross-references inside programs can help us with identifying functions, and residual strings can be used for attribution or indicators of compromise. So for example, for this sample, we can run strings n20 and then we can find peggle, right? And actually, this is also sufficient for us to answer question number 2, right? There's a compilation artifact that reveals the name of the person who wrote the malware. Can we just take a short 30 seconds to run strings, stare really hard and see what we can get? Compilation artifact. So this should be a file path or maybe some Lucas Tan YJ. Does anyone know who Lucas Tan YJ is? That's Samu Zora. That's our web trainer. Yes, he's the person who wrote this malware, apparently. Right? So running strings on this, we will see PopCap Games, Peggle somewhere, and we also see Lucas Tan YJ, and then the PDB, which is the debug file for SharkLoader, right? So that is the compilation artifact that's been left behind, which gives us a tiny bit of information because now we know who wrote the malware, right? Quick question: when running strings, why do I like to run it with n20? What does n20 do? Correct. So it will only show us strings that are length 20 or more, which is useful because a lot of the time some strings, you see, if I don't set n20, right, I get blasted with way more strings, and a lot of them are just really short nonsense strings. This is because sometimes the random bytes inside a program just so happen to be valid ASCII, so then it gets dumped out with everything else. So it makes your output very noisy. So something else I want you guys to try instead, right, instead of using strings, is doing this in Ghidra. So everyone import the SharkLoader binary into Ghidra, right? Just bring it in. Same thing, you guys should be familiar with the steps by now. Drag and drop, hit OK, OK, open it up. Then on auto analyze, yes, analyze, right? Just let it do its thing. Yeah. Okay, I'm assuming most of us have imported or are importing the file right now. So for everyone, I want you guys to go, so after auto analysis is done, I want you to go to window and then defined string. So what you guys should be able to observe in the defined strings window is exactly what we see in strings output. So I'm just gonna expand mine because mine is here. You guys might have it as a detached window, as its own thing. But either way, these are all the strings that Ghidra has managed to identify inside the program. And you see, when you're here, you can do more processing, right? Like you can filter, so I can search for Peggle, and then it will show me all the Peggle strings. I can search for Lucas, and then it will show me the compilation artifact, so on and so forth. Another thing that's notable is that inside this string view, on the left-hand side, it shows me the location where the string is inside the binary. So for example, if I take a look at a lot of these strings like fork or fwrite, you can see they're sitting in strtab, which is short for string table, right? So it's in a different section from .text. Okay, so you guys all managed to see the defined strings, yes? Managed to search through them, look through them. Okay. Before we go on to imports, I want you guys to look at question number 5. Question number 5, right? The malware authors have included fake strings to throw off our analysis. Okay, so we have emphasized a few times that strings are very important in analysis, right? But a malware author knows this, of course. So similar to how Trojans put all the metadata and fake information about a program in, malware authors can also put fake compilation artifacts, fake extra information to try and throw off analysts. So an analyst might see something and be like, oh, he accidentally leaked some information, right? But actually it was intentionally put there to throw you off. So I want you guys to try and look through the strings, right? There are 2 strings which tell you what compiler this program was compiled with. One of them is real, one of them is fake. Okay, it's been about a minute, right? So I heard some answers which are approximately correct, right? So notice at the top of the strings table, we have 2 things, GCC, both of them say GCC. So does anyone know what GCC is? Can someone tell me what GCC is? It's a C compiler. It's the GNU or GNU C compiler for Linux, right? So one string says that it's Ubuntu, right, which is a Linux distribution. Another string says that it's Gentoo, which is a different Linux distribution. Which is the real one? Ubuntu is the real one. Glub, right? So how do we tell the difference? Or at least in this case, what I intentionally did to allow you guys to tell the difference. First and foremost, notice that the Ubuntu one is in the .comment section. The .comment section is the elf comment, and this is strictly defined inside the elf header. So inside the original structure of the elf file, there is a specific section called elf comment, and this is sitting in that very specific section, right? So this is what is usually written there by the compiler itself. If you look at the location of the other string, the gen2 string, notice it is in proton meta. And inside the proton meta section, if we look at the bytes here, actually, you'll notice that a lot of the fake strings that we were looking at, right? All of this nonsense, fake information is sitting inside this section. So it can lend us to believe that this section is just filled with fake information, right? If the Trojan information is in proton meta, then the compiler string that's also there is probably fake as well. Does this line of logic appeal to everyone? Or does anyone have any objections to it? So that clears those questions first, right? Next thing that we're going to answer, what libraries does the malware use? So does anyone remember how we saw what functions were being imported earlier? Symbol tree. So under symbol tree imports, then what could we see earlier to see all the functions that are being imported? External, right? So external shows us all the functions that are being imported. But how do we know what libraries these functions are coming from? I'll give you 20 seconds to think about it. I want you guys to rely on Ghidra here. Don't rely on strings, because the strings, we have just shown that strings can be fake, right? Ghidra has a source truth here. You're going in the right direction. .so something, right? Can anyone tell me where they see anything that goes .so something? In the symbol tree, we have imports, then external, right? Just now we were looking at external to see all the functions. But actually under that, we had libc.so.6 and libcrypto.so.3, right? If you do a Google search for what those are, right, it will give us a bit more information. If I Google what is libc.so.6, right? libc, core system library, the GNU-C library or glibc. And if I do libcrypto.so.3, you can see I Googled this yesterday, right? What library is this? This is a core shared library belonging to OpenSSL. So these are the two libraries that are being imported, right? The answer to this question on the worksheet, right? What are the two libraries that are being imported? libc, which is the GNU-C library, and libcrypto, which is a cryptography library from OpenSSL. Another way that we could have noticed this, right, is if we looked at those external imports, notice how they actually tell you where they're from for some of them. For example, AES, the AES function at OpenSSL, which means it came from OpenSSL. Or malloc at glibc, so it came from the glibc library. Computes for everyone? Makes sense for everyone? So yes, another way of doing recon, right, to understand what libraries were being imported is by looking at the import section, and instead of just looking at the external functions that come in, you see what these libs, right, what these libraries that are being imported are. So this is really important in gaining a high-level view of what actions the malware does, right? If we see it's importing crypto, which we just saw libcrypto, right, that means it's maybe using encryption or decryption or encodings. So maybe it's encrypting files, maybe it's encrypting communications, right? Educated guesses. If we see networking imports, so we see a lot of imports to like HTTP parsers or like sockets or request constructors. Maybe it's communicating over the internet, maybe it's sending commands over the internet, maybe it's accessing online resources. Right? If we see a lot of weird memory related imports, maybe it's trying to hide processors, maybe it's trying to inject into processors. Right? This makes sense to everyone? Right? At a high level, it's like if you see a Python script and the Python script has import math and it's using it, then maybe that Python script is doing some math, right? You see the Python script import base64. Oh, maybe it got base64 inside. So same thing. I see, oh, this program import libcrypto. So maybe there's cryptography inside. So we're gonna go backwards a bit. So now that we've established the imports, right? What libraries the malware uses, libcrypto and libc. We're now going to ask one more question for now, right? the malware connects to a control and command server, or command and control, depends on which way you want to arrange it, but 3 plus 4 equals 4 plus 3, so it doesn't matter, right? So it connects to some C2 server, and the C2 server has a host name, it has a URL that's supposed to be inside the program, but the URL has been obfuscated. So I want you guys to try it inside Ghidra. I'll give you a bit of time. Inside Ghidra, go back to the main function if you've got how to go back there. Go to functions, then functions, go to main. So inside the main function, I want you guys to look at the first few lines of code. And at the first few lines of code, I want you to see if there's any interesting functions being called and if there's any interesting data being handled. So again, focus on the global variables and focus on the weird functions that are being called and tell me if there's anything that pops out that might have to do with the C2. So with your stellar 100 words per minute at minimum, right, get host by name is a networking function used to resolve a host name to get its IP address. So you pass in a host name or a URL, and then what comes out is an IP address. So let's do a bit of renaming, knowing that what we pass in to get by host name is get host by name is a host name. What should I rename local 188 to? Host name. How do I rename? Press L, right? I press L, then I turn this into host name. Okay, cool. So this is probably getting some IP address. And then if I scroll down a bit, this is later used in a connect call. So like it's a bit messed up here, but this is used in a connect call later, right? So it gets an IP address that it tries to connect to it. Okay, cool. So that's probably our command and control server, yeah? Next thing, what line of code is where we are setting the value of hostname? Just say the line number, because we have line numbers. Where is the value of hostname being written? Line number 44, right? Line number 44 is where assignment is occurring. And on top of that, it is in a for loop, right? For loop, local 2e for loop a bit ugly, right? Let's rename it. Let's just rename it to I so the for loop looks cleaner. Okay. So now we can see hostname is being constructed in a for loop. How many times does this for loop for? How do we know it's 15? Actually, it's not 15. How many times does this loop go for? 16. For I equals 0, I less than right click, I less than 15, I plus 1, right? Is it 15 or 16? This is 15. Oops. 0 to 14. Ooh, sorry. I failed math. That's not true. I didn't fail math. But okay, yeah, 15. It's of length 15. So hostname is being constructed by going in this for loop, goes character by character, constructs a 15 character long hostname. And you can see what sort of variable is this? Local or global? Global, right? So if I double click it, it will show me the data on this side. And it is going character by character, and it's performing an XOR operation against 0x5a. So what sort of obfuscation is this? It's a form of data obfuscation, but what obfuscation is it? Like data obfuscation is it? Encrypt. This is an encrypted string. It's an XOR encrypted string. So what we can do to decrypt it is we can use our good friend CyberChef, because we know it's XOR encrypted. So same thing. First thing I want you all to do, highlight, right? Get to the global, then highlight it here. Whole thing must be green. Whole thing must be green. Hijau, right? Right click, copy special. Now instead of doing Python byte string, I want you guys to just do normal byte string. Then I will go back to CyberChef and I will paste it in as my input. You guys should now see a hex string inside the input that looks like this. Everyone see this? If you manage to get the byte string into CyberChef, now what we're gonna do is we're gonna go from hex, because this is hex, right? And then you can see this is the thing that we tried to copy out. Okay, next thing, we know it's XOR, right? So in CyberChef, we're gonna look for XOR. Then can anyone tell me what the XOR key is? 0x5a. There you go. Now we XOR decrypt, and we get an output. And okay, we get an extra character from here. we get an output. So this is our C2 address, c2.sharknet.ctf. So you see, this is, so like when we're doing malware analysis, right? If we want to know what it's connecting to, where it's connecting to, without having to run it, then we would statically analyze it like this, right? We would go into the file, we would see precisely where it calculates or where it evaluates where the C2 server is supposed to be, and then we try and extract the URL ourselves, right? It just so happens to be that for this sample, the string, so the URL that it's connecting to, has been encrypted. So we need to decrypt it ourselves so that we can see what it is. Everyone clear on this? Okay, so why do we do this, right? Okay, so the C2 addresses are very important indicators of compromise. So remember what I said just now, right? If you are running a company and then you start seeing suspicious connections to a certain website, right? If you can isolate what that website is ahead of time and then block it, then you can block some of the connections to the malicious server or the attacker, right? This aids us in this process called attribution. Because if I see that all the C2s are registered from one country, right? They're registering domains from Russia, they're registering domains from China, right? Or I see that the servers that are behind these domains are all clustered in certain countries. All the servers are registered in Brazil. All the registers are registered in Israel or something like that, right? It might give us more information about where the malware might have come from. And when you do this at a very, very large scale, right? It becomes very useful to let us map out where all this malware is coming from, who is writing the malware, and where it's connecting to. So who here has used the website VirusTotal before? 1, 2, 3, 4. Okay, I only see 5 hands. So VirusTotal, this is a very useful website as well. Like this is just good general knowledge. VirusTotal is a website which scans the files that you upload and scans it for malware. So I'm gonna take the malware that I downloaded. This is the one I downloaded yesterday. I'm gonna drop it in because then it'll be faster, right? So when you drop in a virus, it will scan it with all these different antiviruses, and then it'll tell you what it detects. So like for example, this malware that I uploaded is a Mirai sample that came from Malware Bazaar. It's such a shame that only 3 of the antiviruses actually detected it as such. But this is the sample that we have, right? Now another thing is looking at the behaviors of this sample. You can see the traffic, so you can see where it's trying to connect to. So for example, here we can see it's connecting to this IP address, and there is a possibility that this IP address is connected to other things, right? So you see this IP address seems to be safe because well, the community score for it is rubbish actually. If we look at the IP address, and we can search for IP addresses on VirusTotal, what happens is it will actually show us all the other files that have been uploaded to VirusTotal before that either refer to or have connected to this particular IP address. So think about it this way. If I have an IP address, my malware connects to it, then I go to my database and I see all of these other files are also connecting to this same IP address. Then there's a chance that all those other files are related to the same malware that I'm analyzing now. Does that make sense? Because they share a common indicator, and that common indicator is this IP address that is trying to connect to. So yes, that's attribution, right? That's a very, very important part of malware analysis in the industry. And this is what we were talking about earlier, fake metadata, right? So we should have been able to clear some of these questions. We're going to move on to binary analysis, okay? So there are 2 questions. The second one is a bit abstract, I'm sorry, but we'll try and answer the first one first. So just by looking at the main function, I want you guys to tell me what encryption algorithm we think this malware uses, just by looking at the main function. AES, correct. So if we take a look at our main function, we should see a few different types of algorithms being used. So base64, that's encoding. JSON lookup, right? Does anyone know what a JSON file is? A JSON file is basically a dictionary. It's like a dictionary. So if you're familiar with dictionaries in Python, JSON files are just dictionary but in text form, right? Hashing algorithm, so SHA-512 is a hashing algorithm, and AES, so I couldn't fit it in the same screenshot, but like if you scroll down, you should see that AES key and AES IV are being set. And if you inspect any of the other functions, right? So like if you do a quick inspect of decrypt, for example, you should see AES being mentioned. And if you do a quick Google search for what AES is, AES algorithm, this is the advanced encryption standard. So this is an encryption algorithm that we're using, AES. So what point am I trying to drive home with this, right? Malware very rarely uses its own bespoke algorithms or these sort of things. So like when it's encrypting, there's no reason for malware authors to reinvent the wheel every time they want to encrypt something. They will use existing algorithms that exist, like RC4, RSA, AES, ECC, Blowfish, right? For example, 2017 WannaCry, right? The WannaCry infection used RSA and Blowfish to encrypt your files. So they're not coming up with new algorithms, right? Other smarter people have already done it. They can just use it. And structured data formats like JSON, all that, they don't have to reinvent data formats every time they want to use something, right? So they can just reuse JSON. So for example, encodings, we've looked at base64 and hex a lot already. There's also URL encoding and so many other encodings that we can do. And remember that these are all representations of the same data, like different representations of the same data, right? And malware authors can just use different encodings here and there when they see fit. Structured data, right, to organize data that's being sent. So keep in mind, this is a remote access Trojan. Even though like malware doesn't have to be clean, when you are sending commands down to your Trojan and receiving data from your Trojan, you want the commands you send and the data you receive to be structured so that it's not so messy and you don't have to take so much time to understand what data you're pulling from it. Cryptographic algorithms, like I said, right? Hash algorithms, encryption algorithms, so on and so forth. They're used and abused in many ways, and malware authors won't reinvent the wheel every time they want to use one. Okay, and now this is the really, really complicated part. So what encryption algorithm is being used? AES. What formatting does the malware use to package its commands? This one, weird abstract question, but it is JSON. So notice that it uses JSON lookup here and there, right? So the structured format that it uses is JSON. And in fact, just by looking at strings, we can see a lot of JSON strings. So like this, you see this here? This looks a lot like a Python dictionary, right? Agree? Agreement? Yeah, so this is what a JSON structured query looks like. So it has a key operation and a value key exchange. A key, nonce, and a value, which in here is %s. And if I just filter by curly brace, I should be able to see all the different commands that this malware actually has implemented, right? So I can see a heartbeat command, I can see a fingerprint command, shell, list directory, download, upload, process list, sleep, key exchange, right? These are all plain text strings which are involved inside the communications of the malware that are using a structured format, and the structured format is JSON. This is the JSON format. Okay, so this part is very complicated, and I need you guys to follow along very, very carefully. Because if you don't follow this part, right, you're gonna get lost for the next few functions. Okay, Ken? So what I'm gonna do now, I'm gonna go back to my decompiler view, gonna go back to main, right? So this is, I want you guys to just listen to what I'm saying, and then just follow the instructions, Ken, right? And if you're unclear or if you want me to clarify why we're doing something, then just say, Ken. So what we're going to do now is we're going to understand how the malware is running. So our conception of a remote access Trojan is that an attacker will send commands to our computer. Then after it sends commands, then the program will do specific things based on what those commands are, correct? The thing is, those commands have to be implemented somewhere inside the binary. So we want to find what functions those are, and we want to name those functions so that we can analyze them deeper. So the first bit of logic that is very relevant here is all the way down here. So if you go to your main function, and scroll down to line 131, right? At least line 131. This is a while true loop. So can someone tell me what a while true loop does? It just keeps looping forever until it breaks out of it. So this is the main processing loop of the program. And then the next thing I want you guys to see is this JSON lookup function. Can you all click on the global and tell me what the value is? It should be a 2-character string. OP. So you see over here, this global variable is just a 2-character long string, which is OP. So I'm going to rename it to s_OP so that I know it's the string OP. So just now when we looked at a lot of the strings, right, we could see that in the JSON format, they all have OP is something, OP is something, OP is something. Do we want to guess what OP stands for? Operation. So OP defines what operation the malware is trying to perform. What this chunk of code is doing, and this one just trust me on it, just believe what I'm saying, is it receives the command from the attacker, and then it turns it into JSON, and then it will pick the command using the selector OP. So it'll get the command. So local 2A8 here, right? Local 2A8 is the received packet. Local 2A0, I want you guys to rename this with me. Local 2A0 is the command ID, or like the name of the command that was being sent from the attacker to the computer. Okay, next thing, there's a for loop here. For loop always a bit ugly if we just leave it as local. You cannot rename it to I because we used I earlier. So we just pick another single character, let's do J. So now we have a for loop. So I want you guys to look at what this for loop is doing. So we have our command ID here. Then inside our for loop, it is using strcmp. What does strcmp do? String compare. It compares strings. So our command ID is a string, and it is comparing it against this. So this is an array, right? This is an array. How do we know it's an array? Because we are doing square brackets and then accessing something. Make sense? So if we are comparing strings, this means that this global, we double click it, we can see in this global there's a bunch of strings there. So this must be a string array. So I'm going to rename this to command string array. So notice inside this for loop, right, it does j times 2 in the for loop. What does this mean? Like when I'm going through an array, and then I'm doing index times 2, index times 2, index times 2. What's the notable aspect of this in a for loop? 0, then 2, then 4, then 6, right? So that means it's skipping every odd entry, correct? So if I double click on this global, I want you guys to notice. So imagine, I know this is very hard to visualize because this is not how you guys are usually used to looking at arrays. But I want you to imagine that all of these entries here, I want you to imagine these entries here are entries in an array, can? So then entry number 0 is? What's entry 0 in this array? S heartbeat, right? Entry number 1 is fun 00103 right? Entry number 4, index number 4 in this array is 0, 1, 2, 3, 4. Shell, right? What is entry number 2? Index number 2 in the array? Fingerprint, right? So when I am doing in jumps of even numbers, right, I'm going S heartbeat, S fingerprint, S shell, then I go down, S list dir, S download, S upload, S process list. No, the rest is not junk. So you see, we're skipping entries, right? But those entries in between are not useless. If you were to double click on any of the in between entries, what you will notice is that they are functions. That's why they're called fun, because functions are fun. But yeah, they're functions. So why is it that there are functions in between the strings? Let's look let's go back to main. I want you to look at the next part of the code. And then if you double click on this global, you'll notice we have now landed here, in between. I double click here, I land here, right? What this is another array. This isn't a string array. This is a, I'm gonna label it command function array. So this is quite a advanced idea, I guess, right? And notice how we're doing skips of 2 again. So our first entry is fun 00103419. Our second entry is fun 00103443, right? Now instead of jumping over the functions, we're jumping over the strings. So what is the purpose of this, right? Let's say I do string compare, right? I do string compare against my command ID, and my command ID matches with the string heartbeat. So then my j value is j equals 0, right? Correct? Correct. Right? It's j equals 0 because it's the first entry. Then it will go into this part of the loop, and then it will take the first entry of the function array, which is this function, and it will run the function. So that means if my command ID is heartbeat, it will run this function, and this is the heartbeat function. If I go again, right? Let's say instead my string compare, command ID, and then I compare it against the strings here. Let's say it managed to compare with index number 4, right? J equals 4. So 0, 1, 2, 3, 4. The S download string, right? The download string. So then same thing. Then it will enter this part of the loop. Well, it'll pass this if statement. Then it will pick the fourth function. So it will go same thing. 1, 2, 3. Okay, wait. Off by one. So 0, 0, 1, 2, 3, 4. So that means this function will get called if the command ID is download. And this, if you look at the strings here, you see download response. So this is some like really evil tech, right? But this is something that malware authors do all the time, right? This is another form of obfuscation, a much more advanced form of obfuscation called control flow obfuscation. So before we do more renaming, I want to check that everyone has renamed their variables to look like this, right? Hopefully you guys have followed along diligently as I've been renaming stuff. Okay, so assuming everyone has managed to clear this section, I'll now explain with a few more graphics what I mean by control flow flattening, right? So this is what control flow is, right? Control flow is a way for us to visualize or at least to understand how the flow of programs is like. So for example, this very basic if statement, you can think of an if statement as literally having 2 branches, right? So like if x more than 2, true, false, right? So then each true and each false produces a branch, and then the control flow of the program will look something like this, right? It's either you flow this way or you flow that way. So this is very useful for analysis a lot of the time, because let's say you have a giant program, and then you have all of these different flows, right? Like never mind. You can start your flow from the start, then you keep flowing through the program and seeing the different blocks that it goes through until it reaches the end, right? And it will give you a better view of how the program runs. So this was what we were looking at just now, right? The renaming is a bit incomplete in this screenshot, but that's what we were doing just now. What I want you guys to think about is how the program traditionally would have been written. If you were not trying to obfuscate control flow, you would have just done a giant if statement, right? You have just done if command equals thing, run this function. If command equals thing, run that function. Does this make sense to everyone? Like this is how you would have written a command dispatcher if you were a normal person, right? And then your control flow is very linear. It goes command ID, check if it's equal to this. Okay, it's equal to that branch. No, it equals to something else. Go down. Okay, branch, right? Very straight, very easy to analyze, right? Because it's just a bunch of if statements. what we made just now is a for loop, and then we shoved all the all the if statements into a for loop. So you see, our very nice branch like that control flow got flattened out and turned into branch like that. So like, I know this graphical okay, does the graphical representation help? Like, does this explain how this complicates things? Wow, that's a weird phrase. Does this explain how it complicates? But like, yeah, this is what traditional control flow would look like. This is what obfuscated control flow, which is what we were looking at just now, looks like. Ken? In its most extreme form, this is what a control flow flattened program looks like. So this is a legitimate malware sample that has been obfuscated with VM Protect. And the output control flow graph looks something like this. So all the actual logic in the program has been flattened out, and every time it needs to do anything meaningful, it will jump back to one big dispatcher, and it will jump to the correct thing in a for loop, so on and so forth, so on and so forth. So this is very, very hard to analyze, right? Because it's not clear how the pathways inside the program flow. So now that we have determined that this is control flow obfuscated, we can isolate the functions that are being called still, right? So remember what I was saying. In the string array, it's heartbeat, right? What is the entry that follows it? It's the function that gets called when you receive the command heartbeat. If I receive the command fingerprint, the function that gets called is the entry right after it. So actually, we can do a lot of renaming right now, right? What you can do is, if you go to the command string array global, and then you double click on any of these functions, right? You can now start to rename them because you know what they should correspond with. They just correspond with the string above them. So like this one, I'm going to rename it to heartbeat. I'm going to select L, then rename this to heartbeat resp, right? Or I go back to my array, fingerprint. After fingerprint, I want to rename this function to fingerprint resp, fingerprint response, right? Not resp, response. So this is a bit tedious. I will now leave you guys to do this tedious task. So just slowly go down the function table, and then for each function underneath the string, right, rename it to reflect that it's the response to that command. Ken, this make sense? When I'm back, everyone should have these labeled. So you guys should have renamed a bunch of the functions. So now that means I can refer to the functions without you guys getting lost, hopefully, right? So let's start looking at the individual functions that are inside our program, right? If we go back to the worksheet, we're going to be looking at 3 of the functions in particular, right? First function that we're going to be looking at, process list response. So from the function table, go over to the function that you have renamed that corresponds to the process list. It should be right underneath the string process list. And you should be dropped into a function that, to verify that you're in the correct function, the first few lines should look like this. Okay, anyway, so this should be the function that you should have been able to identify to be process list response, right? I want you guys to look at the first few lines and do a bit of Google searching if you have to, right? I want you guys to ask the question to yourselves, how does it get the list of processors on your system? So you can see the weird sort of stuff it does here, right? It opens a directory called /proc. Now the magical thing in Linux is everything is a file. So even the process list that the kernel maintains is a file. In this case, it's /proc. And then /proc, not just that, it doesn't just give the list of process IDs, it also gives you the list of process names if you ask really nicely. So this line of code over here, right? It does /proc /something/com. What it actually does is it requests for the command name. You can Google /proc/com, and you should be able to find the man page which talks about getting the command name from /proc. So the process list function is able to extract the process list by querying /proc. And what I want to raise as a point here is this is a system-specific way of getting the process list, right? On Linux, if you want to get the process list, you need to read /proc. If you're on Windows, how would you read your process list? Task Manager, right? This is the equivalent of opening Task Manager on Linux and then reading the processes that are here, right? Except in Linux, you don't have something as fancy as Task Manager. You just read /proc and you're good. Yeah, process list. Process list using /proc to get the list of processes. Awesome. Okay, now download the download response dispatcher function, right? I want you guys to go to your label. I mean, in my case, I call it download resp. I'm gonna look for download resp. Download response function. You should see something that starts a little bit like this, right? And then based on the decompilation output that you see, I want you guys to answer the very basic question, what encoding are they using before uploading the file? Base64. The answer is right there in front of your eyes. Base64. Yeah. So in this case, again, we can slowly step through and see what this function is doing, right? It is reading a file, then it's allocating some memory, base64 encoding it, constructing its response, and then encrypting and sending it. Make sense? Make sense? Make sense? Okay. And now the last question, look at the fingerprint response function, right? I want you guys to see, and you should be able to just see this by strings, like just looking at the strings in the function, right? What data is being collected by the function? So I'm just gonna rapid fire, right? Once you guys are here, the answer should just fall out. Okay, so you can see that it has this structured response that it's constructing, and you can just read off some of the values that it's trying to collect. The host name, the user, the OS, the kernel, the architecture, right? And it's sending this off. And even at the end, we can see that it also makes a request to an IP tracker. So this is an IP grabber website, right? So the thing that I want to point out in particular for this is that it makes use of the functions getenv and uname. Now uname is real neat because you can run uname yourself as well, right? If you're in a WSL terminal, you can do uname-a. And you can see this is all the information that will get dumped out when you call the uname function inside the program. And that's how they're able to collect so much information to send back, right? So information about the kernel, information about the host name, this is my host name, right? This is my architecture, right? This is my OS, the current time even, right? No, that's not the current time, I'm lying. That's the time when the kernel was compiled. So that's kernel compilation information, right? These are all data that you can use to uniquely fingerprint and identify computers that you have infected. Okay, so wow, I sort of sped through that, low-key, which means that we can actually, okay, we've done all this. We can get to the tail end of this program.